Hello, and welcome to the third devlog of my newest Unity project, the World Simulation Project. The overall plan for this is to create a large-scoped grand strategy game, taking place on a fully procedural-generated, tile-based world. This time, we have to dive a bit deeper into the technical details behind my project. This has a simple reason. I had to completely rethink how I want to use Unity's DOTS technology. This led to a complete reboot of the project. Before we start, if you like my content or if you are interested in following the progress of this project, please consider to subscribe to this channel and leave a like or a comment. And if you want to join the discussion about it, or if you like to participate in the surveys I will start in the future, you can join my new Discord server. You will find the link in the description. Now you might ask, why did you reboot your project completely? Didn't everything work fine so far, how I can see in the previous devlogs? True, but when I tackled the task of implementing a selection system for individual tiles, I ran into serious trouble. Let me explain. Let's assume to have a single entity, for instance, a cube. Beside of the components to define the position, the shape, and the material, this cube contains the ECS equivalent of a box collider. What we also have, of course, is the camera. When we want to select the cube to interact with it somehow, we cast a ray from the camera into the world, towards the mouse click position. As soon as the ray hits the collider of the cube, we can detect this and so get the cube to interact with it. No problems so far. Obviously, we don't have only one selectable object, but 100,000 of them, our world tiles. But why is that a problem? As far as I know, at least when using ECS, Unity rebuilds the entire physics world every single frame, probably to update the collider positions and the raycast calculations. This happens in the system build physics world. When checking the system overview, it's obvious that it runs over all 100,000 of entities we have in our world, and that makes the FPS drop below the bedrock level. Minecraft players will know. I tried several things to work around this. For example, by creating a system which holds all selectable entities and their bounds in a hash map and does the raycasting manually. This fixed the overall performance, but needed way too much time for sampling and finding tiles to be responsive. Even parallelizing the process using the job system didn't help. I also tried to turn off this build physics world system, but then the raycasting stopped to work completely. Completely frustrated, I stopped development for a while and asked some people in different communities and Discord servers for ideas. After trying out some of them and failing over and over again, I came to the conclusion that I need to take a step back and think about the greater picture and other alternatives. What I came up with is something you can call a synthesis of Minecraft techniques and Unity's DOTS. This is how the world generation algorithm works now. 1. Based on the predefined total amount, a grid of chunks is generated. All following steps are applied on each chunk in sequence. 2. Each chunk is filled with a predefined amount of tiles. Actually, every tile is an ECS entity and they do not have rendering components at all. After this step, a tile only contains a local transform and a chunk assignment component. Also at this moment, the world still is completely flat. 3. Now every tile is relocated based on the Perlin noise algorithm I already talked about in a previous devlog. 4. Every tile is filled with its properties which are relevant for the game itself. This data, for example, contains the vegetation zone based on the tile height. In the future, this step will be expanded a lot to put many more properties into the tile. 5. Based on the tiles within the chunk, a mesh is generated. Right now this process needs much more optimization, but it works quite good now, so it's something for the future. 6. In the final step, all generated data from the previous steps are applied to a traditional game object. This game object only is needed to render the world and to act as a target for the tile selection system. The result of all these steps looks like this. In case you are wondering about this crazy-looking change of the chunk textures, the shader for them is set up in a way it changes its appearance based on the terrain height and the predefined vegetation zone heights. So when I move it in the Y direction, it thinks its vegetation zone changes and adjusts its textures. With this new world generation process in place, finally I could implement a proper tile selection system. and it's surprisingly simple. It consists of only two classes, Tile Selection System and Tile Selector. The Tile Selection System class is the heart of the thing. It checks at which position the player points with the mouse cursor, finds the nearest tile and tells the selector where to move. When the player clicks on the current position, it sends an event with some data about the tile to the UI manager, which then opens a pop-up window to show the data to the player. The Selector class controls the UI element the player sees in the world. It highlights the tile the player is currently pointing at. This makes it easier to click on the intended tile. To make it a bit more pleasing, the selector shouldn't jump instantly from tile to tile instantly when the player moves the mouse. By using coroutines, it moves smoothly over the landscape. I also created a scriptable object to set some parameters for the system as well. I can adjust the appearance of the selector in general by switching the prefab, change the color tint of it, and how fast it moves across the landscape. But now, let's see it in action. Speaking of scriptable objects, while coding all this stuff, I also created some more scriptable objects to make it easier and safer to define parameters about the world creation. Right now there are 3. The world creation parameters holds the general settings about the world generation process. To make this process more modular, I splitted the process into the steps I explained before. Each of them is a class implementing the iGeneration component interface. All of them I can arrange in the world creation parameters. I know it's not the best way, especially because some are dependent on another and need to be performed in a certain sequence. But for me, it's a bit more pleasing to the eye, and I can, for instance, disable the tile height calculation step to make the world generation faster if I want to test new features which don't need a fully generated world. Then we have the noise parameters. Here I can fine-tune the settings for all the noise filters in the Perlin noise algorithm. I even can add additional ones there, or when I implement them later, add completely new filters which can create shapes in the world which are impossible with the currently existing ones. And lastly, we have the vegetation zone settings. Here I can define which vegetation zones exist and at which height they merge into another. Nothing more to say about it. So that was it for this time. I hope looking at the technical backgrounds was interesting for you. Tell me about your opinion in the comments, and don't forget to like and subscribe if you want to see more. And consider joining the Discord server to get some more details earlier than everyone else. Thanks for watching, and see you next time.